Hey everyone, today we're jumping right into one of the absolute coolest puzzles in modern engineering, how autonomous robots actually manage to navigate a completely unpredictable world. We're going to unpack the incredible concept of probabilistic state estimation and look at how we give robots this kind of Bayesian brain to help them perceive their surroundings even when they're getting fed really imperfect data. If you love digging into how things actually work under the hood, you are definitely in the right place for this explainer.
So I want you to picture this visceral scenario for a second. Your robot is stuck in a pitch-black room. And to make matters worse, it's got a broken sensor. It's effectively blindfolded. How on earth does that machine program any sense of confidence that it's not going to just immediately slam into a wall? I mean, it's a terrifying thought for us humans, but for a machine, this is just a giant mathematical puzzle waiting to be solved. The real question is, how do we translate the abstract, messy reality of sensor noise into a tangible, safe path forward?
To figure that out, we've put together a bit of a cognitive survival guide. We'll be looking at the problem of uncertainty, the Bayesian brain, and the math behind the magic. Then we'll dive into the Stanley case study, the cost of confidence, and wrap up with the myth of certainty.
All right, let's kick things off with Section 1, the problem of uncertainty and dealing with unpredictable hardware.
Here's the brutal truth we have to face right away. Hardware is, well, fundamentally flawed. Sensors fail. They give us messy, imperfect data. And the physical world around the robot, it is incredibly noisy, filled with totally unpredictable variables, like sudden lighting changes, uneven terrain, or obstacles popping out of nowhere. So, the ultimate reality here is that absolute hardware certainty is literally impossible. Because a machine is effectively flying blind relying on this noisy data, engineers can't just trust the raw output from physical cameras and lasers. They absolutely have to turn to software solutions to maintain any high level of confidence while moving. And that software solution leads us right into Section 2, the Bayesian brain, and implementing statistical frameworks. To give robots this highly logical, calculating mind, engineers rely on something called the recursive Bayes filter framework. Think of it as the heartbeat of this entire process. It's basically a continuous two-step loop. Step 1 is the prediction phase, where the robot uses state transitions to essentially guess where it is right now, based on its last known movement. Step 2 is the update phase. This is where it uses probability density functions, pulling in new incoming sensor data to correct that initial guess. So the really crucial takeaway here is that the algorithm continuously cycles: predict, update, predict, update. It is constantly refining its own internal map to pinpoint exactly where it's at.
Moving right along to Section 3, the math behind the magic, taking a closer look at the core algorithms.
Okay, I know, the word algorithms can sound a little intimidating, but let's unravel this mystery one clue at a time. The first key is a concept called Markov chains. Simply put, this is a mathematical system where transitions from one state to another depend solely on the current state. It completely ignores the past sequence of events. And think about how brilliant that is for a robot's processing power. Instead of needing to remember every single inch it has traveled since it booted up, this logical deduction lets the robot drastically simplify its processing load. It really only needs to focus on its immediate present state to figure out what happens next. To put that kind of efficiency into perspective, just think about the number 3. When utilizing these statistical frameworks, it might only take exactly 3 sensor pings for a robot to calculate a highly accurate probability of being at a specific spot. Let's call it position X. It doesn't need 1,000 data points to make a good, educated guess. It just needs a few rapid-fire loops of predicting and updating to completely lock in its location.
Now this builds directly into how we actually handle the errors themselves, using Gaussian noise models. These are statistical models that represent sensor error as a normal bell curve distribution. Since we've already established that sensors are far from perfect, Gaussian noise models are how the robot mathematically boxes in the standard margins of error in its environment. It basically tells the robot's brain, hey, your true location is highly likely to be right here in the fat middle of this curve and extremely unlikely to be way out on those distant edges.
And what happens when you translate that bell curve into physical space? You get what's called the confidence ellipse. Imagine a 2D bubble of uncertainty drawn completely around the robot on the map. When you first turn the robot on, that bubble is massive. It could technically be almost anywhere. But as it takes those 3 pings, as it runs that recursive Bayes filter, that bubble starts to shrink. As the robot continuously updates its data, the math tightens up and the machine becomes vastly more certain of its actual spatial location. It's a really elegant solution.
But, as we know, robots don't usually move in perfectly simple straight lines. So we need to compare a couple of distinct filtering tools used for more complex paths: the Extended Kalman Filter, or EKF, and the Unscented Kalman Filter, or UKF. The EKF uses linearization to estimate complex curves, basically drawing tiny straight lines to guess the path of a curve. But the UKF handles highly nonlinear models without explicit Jacobians. It's just a much more advanced way to calculate wilder, chaotic movements. Ultimately, engineers have to select different filtering tools depending on the specific mathematical complexity of the environment the robot is going to face.
Which perfectly cues up Section 4, the Stanley Case Study, and winning the DARPA Grand Challenge.
All right, it's time to take all this abstract math theory out of the lab and look at a massive, high-stakes, real-world payoff. Back during the historic DARPA Grand Challenge, completely autonomous vehicles had to navigate this grueling, totally unpredictable desert course. And you know what? Most of those vehicles failed spectacularly. But Sebastian Thrun's car, named Stanley, actually won the whole thing. How? By applying these exact probabilistic state estimation techniques we've just been talking about. The vehicle didn't just blindly trust its sensors. It used Bayesian logic, Kalman filters, and recursive estimation to literally perceive the desert environment, totally cutting through the dust, the massive bumps, and all that raw sensor noise. However, achieving that level of autonomous brilliance certainly isn't free. Welcome to Section 5, the cost of confidence, where we look at the engineering trade-offs. Computational confidence comes with a really hefty price tag. Take something like a particle filter, an advanced algorithm that generates thousands of virtual guesses of where the robot might currently be. When weighing the trade-offs for a 1,000 particle filter, there is an incredibly high computational cost. It totally drains the battery and requires massive amounts of processing power. But right alongside that, you get the payoff of high localization accuracy. Engineers are locked in this constant tug of war, having to weigh these two factors against each other. How much raw processing power are you actually willing to sacrifice just to get pinpoint accuracy?
And of course, there are traps along the way. The absolute biggest pitfall is assuming sensor noise is always going to be normal or Gaussian. While the math behind it is beautiful, the real world is incredibly messy. Real-world anomalies like a sudden flash of blinding sunlight directly into a camera lens or a crucial sensor getting completely caked in thick mud, those are extreme outliers, and they absolutely do not always fit perfectly into a neat, predictable bell curve.
What's really brilliant about all of this, though, is how interconnected these technologies actually are. The robotic concepts we're discussing map directly onto everyday data science and machine learning roles. Handling incredibly noisy datasets, generating accurate machine learning predictions, general algorithm optimization. These rely on the exact same Bayesian frameworks. They're just applied to massive data streams instead of physical desert roads.
Which leads us to our final stop for today, Section 6, the myth of certainty and the true limits of perception.
We've gone from blind uncertainty in a pitch-black room to brilliant probabilistic estimation. But I want to leave you with one final, kind of provocative question to chew on. Is absolute certainty in robotics actually just a myth, given that hardware is inherently flawed and software is at its core fundamentally just making highly educated statistical guesses? Will a machine ever truly know exactly where it is? It's a totally fascinating theoretical limit of machine perception to ponder. Now, if you want to dive even deeper down this rabbit hole, I highly encourage checking out the recommended reading, Probabilistic Robotics by Thrun and his colleagues. Thanks so much for hanging out with me for this explainer. Keep asking those great questions, and I'll catch you next time.